Video is on Cartesian products of sets. An ordered pair x comma y is a list of two elements x and y. The order of these elements does matter, so the ordered pair 3, 7 is different from the ordered pair 7, 3. Remember, that's not like how it is in a set. So in a set, for example, the set 3, 7 would be equal to the set 7, 3. And remember, sets have braces. These ordered pairs have parentheses. Also, the term list also denotes order. So an ordered pair can have things like numbers in it, like the two above. It could also have just any kind of object in an ordered pair as an element. So for example, this has 4 as our first element and the rational numbers, the set of all rational numbers q as the second element. The next ordered pair that we see has an ordered pair as an element, and then the number 0.8 as its second element. So both of those are examples of ordered pairs. Given two sets, A and B, the Cartesian product of A and B is a new set, and that's denoted A cross B, the Cartesian product of A and B, and it's the set of ordered pairs A comma B such that the first element of the ordered pair is in the first set, so A is in A, and the second element of the ordered pair is in the second set, so B is in the set B. As an example, if A is the set 2, 4, and 6, and B is the set T and 5, then the Cartesian product of A and B would be 2 comma T, 2 comma 5. So those are both elements where 2 is in A and T and 5 are both in B. 4 comma T, 4 comma 5, 6 comma T, and 6 comma 5. So that's the Cartesian product of those two sets. The Cartesian product is a set of ordered pairs. And so remember that the order of elements in a set does not matter. So the order in which the ordered pairs does not matter. I'll say that 3 times fast. So these two sets are equal, despite that the order in which the ordered pairs appear is different. So here's 2 examples for you to try. So if we let C be the set containing 0 and 5, and D be the set containing -1 and 0, then I'd like you to give me both the set C cross D and the set D cross C, each of those Cartesian products. And second one for you to try, a more general question. So just for any set A, if the cardinality of A is K, if A has K elements, and the cardinality of B is M, what is the cardinality of A cross B? So I'd like you to pause, grab some paper if you don't have it already, write out some solutions for those, and we'll talk about those in just a moment. All right, so let's first find C cross D. So C cross D is the set of ordered pairs where the first element is in C and the second element is in D. So 0 is an element of C and -1 is an element of D. 0 is an element of C and 0 is also an element of D. 5 is an element of C, and -1 is an element of D, and 5 is an element of C, and 0 is an element of D. So that would be C cross D. D cross C is going to be very similar, just the order of the ordered pairs is going to be opposite. So D cross C, we have elements of D first, so -1 comma 0, -1 comma 5. Negative ones we've already got, so 0 comma 0 and 0 comma 5. So that is D cross C, and these two sets are not equal. So in general, C cross C is not generally equal to D cross C. And in general, if the cardinality of A is K and the cardinality of B is M, what is the cardinality of A cross B? So we saw 2 examples above. So we had one example up above where the cardinality of A was, so above we had an example where the cardinality of A was 3 and the cardinality of B was 2. And we ended up with 6 ordered pairs in that case. The cardinality of A cross B, if you take a look above, was 6. In this example we just saw, the cardinality of C was equal to 2, which was also equal to the cardinality of D. And we saw that then the cardinality of C cross D was 4. So you might, hazard a guess from there that maybe the cardinality of A cross B is equal to the cardinality of A times the cardinality of B. Or in other words, here we assume that cardinality of A is K, cardinality of B is M. That would be K times M. But how could you argue it more effectively? Well, let's think about it as, the set of ordered pairs. So if we have, A1, A2, ... up to AK, and B has the elements B1, B2, ... up to B sub M, then this gives us the ordered pair A1, comma B1. This gives us the ordered pair A1, comma B2, and so on, A1, comma BM, and down to AK, comma BM, AK, comma B1. So this gives us, this set of ordered pairs. How many of them are there? Well, there's K in this direction, and there are M in this direction. So this is an M by K rectangle of ordered pairs. There are K times M ordered pairs in the set A cross B. A Cartesian product you're probably familiar with is the Cartesian plane. So that's the xy plane, and R cross R is the set of all points on the Cartesian plane. So if we take the standard approach that this is the first value in the ordered pair, x-axis, and the y-axis gives the second value in the ordered pair, then x comma y is all points x comma y, such that x is in the real numbers and y is in the real numbers. So it's everything on that set. If we can't really draw it, it's everything. How about the set R cross Z? So those are elements such that, ordered pairs such that the first element is in the real numbers and the second element is an integer. So these are the integers, remember? And so if we wanted to sketch that set, what does that set look like? So the x values are in the real numbers. So the x values are anything on the x-axis, and the y values are in the set of integers. So the y values can be 1, 2, 3, and so on, and also 0, -1, -2, -3, and so on. And so this set is going to be, x can be anything, so x is the whole number line, but y can only be integers. So if we were sketching this set, it would look like infinitely many horizontal lines. So this is what the set R cross Z would look like. So here's a couple examples for you to try. So I'd like you to draw sketches of the following sets on the xy plane. I'm going to not read those out loud because part of the idea is to remember what those symbols stand for. So I'm going to pause and let you try those. All right, let's look at the set n cross r on the xy plane. So these are the natural numbers. And remember that the natural numbers start with 1, and then 2, and then 3, and so on, all positive integers. And these are the real numbers. So that's everything on the xy plane, everything from negative infinity to positive infinity. So if we're sketching this on the xy plane, then this is also, let's also write it as a set. So this is x comma y, such that x is in the natural numbers and y is in the real numbers. So the values for x can only be natural numbers 1, 2, 3, 4, etc. The values for y can be any real numbers. So this, if we sketch it, will look like that. And it goes on forever in the positive direction, but there are no there's nothing at the line y equals 0. X equals 0. There's nothing at the line x equals -4, etc. So that's the sketch for that. Next, we want to sketch z cross n. So again, these are the integers. So those are positive and negative whole numbers as well as 0. So dot, 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 -3, -2, -1, 0, 1, 2, etc. And these are the natural numbers as we have above. And so z cross n as a set is the set of ordered pairs x comma y, such that x is in the integers and y is in the natural numbers. So what elements are in that set? So for example, x is -2, y equals 1 would be an element of z cross n, because -2 is in the integers, 1 is in the natural numbers. We again assume that we're just on the regular xy plane for all of these. And so if we're sketching this on the xy plane, then x is -2, y is +1. That would be one such point. This would be another point that would be in there that would satisfy those properties. And we'd have this like line of dots. So we no longer have lines horizontal or vertical, but we have dots. So for example, the point 1, 2, 3, 4, the point 2, 4 would also meet the criteria that 2 is in the integers and 4 is in the natural numbers. So basically we just have this infinite array of points at values where the x value is any integer and the y value is a natural number. And that would be what our sketch would look like. Finally, the set 1, 2 cross the set containing -1 and the set containing 3. So notice that these are very different sets. So this is an infinite set because it has infinitely many values from 1 to 2 inclusive. So this is an infinite set, whereas this is a set with 2 elements. And those 2 elements are the number -1 and the number +3. So this has infinitely many elements, and that has 2 elements. Again, this is the set x comma y, such that x is an element of the set from 1 to 2, that closed interval from 1 to 2, and y is in the set of 2 elements, the elements -1 and +3. So that's the set if we're writing it in set builder notation. If we're drawing it on the xy plane, so x can be anywhere between 1 and 2. Y can only be 2 different elements. Y can only be 3 or -1. So now we've got some horizontal lines, the line from 1 to 2 inclusive at y equals 3, and the line from 1 to 2 inclusive at y equals -1, and that is our set. Here's just another example of a Cartesian product of 2 sets. So z cross the Cartesian product c cross n. Here, this is a set, and it is also the Cartesian product of 2 sets. So that's the set of ordered pairs of the form x, comma, y cross z. So this is one element, and that element is an ordered pair. And because of the parentheses here, we would also have these parentheses here around each of those elements, which again are ordered pairs themselves. These are from the Cartesian product C cross N. We can also have ordered triples, ordered n-tuples, etc. So x comma y comma z is an ordered triple, and it is different from the kind of thing that we see above. So above we saw something of the form x comma in parentheses y comma z. So this is an ordered pair, So this is an ordered pair where the second element of the ordered pair is itself an ordered pair. And similarly, this is a different ordered pair. So each of these things are not equal to each other. They're all different types of elements. And an ordered triple x comma y comma z, that's again just from some Cartesian product of sets. A cross B cross C would be x comma y comma z, such that x is in A, y is in B, and z is in C, whatever those sets happen to be. We can also have ordered n tuples. So we have ordered pairs, ordered triples, ordered 4 tuples, ordered, whatever, n tuple for any value of n. And, well, I suppose not exactly any value of n, n in the natural numbers. That would be an n tuple. And we can take the Cartesian product as well of more than 2 sets. So that's sort of alluded to here. We can take the Cartesian product of any number of sets that we like. So A cross B cross C would be a set of 4 tuples. So that would be A comma B comma C comma D, such that A is in A, B is in B, C is in C, and little d is in D. So that would be a set of 4 tuples. Finally, we can also take the Cartesian powers of sets. So we see that Cartesian product is kind of like multiplication. Remember that if the cardinality of A cross B is the cardinality of A times the cardinality of B, and in some ways it sort of looks a little like multiplication. Cartesian powers of sets, exponents. So if A is a set and n is a natural number, A to the n is the Cartesian product of A with itself n times. So this is A Cartesian product with itself n times. So here's 2 quick ones to try. If we let A just be the set containing the elements A and B, then I'd like you to find A to the 3rd power. And now a general question. If the cardinality of A is K, what will be the cardinality of A to the n? So think about those and we'll talk about them together. Okay, so A to the 3rd is A cross A cross A. So those are ordered triples. So A comma A comma A would be an element where A is in the first set, A is in the second set, and A is in the 3rd set. It's in each of those sets. Another element would be A comma B. Another element A comma B comma A. Another element A comma B comma B. Another element B comma A comma A. Another element B comma A comma B. B comma B comma A. And finally B comma B comma B. So those are the 8 elements in the Cartesian product of A with itself 3 times, the 8 elements of A to the 3rd. And remember that the order of the elements does not matter, so if you'd put, this first and that second, that would be fine. If the cardinality of A is K, what is the cardinality of A to the n? So again, you might have gotten a hint from above. Note that in this example over here, the cardinality of A happened to be 2, and the cardinality of A to the 3rd was 8, which is 2 to the 3rd. So there are 8 ordered pairs when we write them all out. And in general, it's the case that if the cardinality of A is K, then the cardinality of A to the n is going to be K to the nth power, or in other words, it's the cardinality of A to the nth power, whatever that is. And we can think about that sort of inductively. If we think about A to the n is A cross A cross A cross A n times. We could think about that sort of, one at a time. A cross A gives us, so these two together gives us A the cardinality of A times the cardinality of A, k squared. When we do another, that'll give us k cubed, and so on. So we saw that each one individually multiplies the cardinality. If we're multiplying the cardinality n times, we would get the cardinality to the nth power.